Our next topic is hypothesis testing. So we've been doing confidence intervals, and confidence intervals are used when only parameter estimation is required. Okay, so hypothesis tests kind of take that a step further, and they're used when you have some kind of prior idea, and you're going to gather data to test that idea, and then you're going to evaluate the evidence regarding your prior idea. The hypotheses themselves are statements about population parameters, and they must be specified before the data is collected, because they're the reason we're collecting the data. There's some prior idea that's going to be tested, and the hypotheses are the prior idea. Hypotheses always come in pairs. There's a null hypothesis and an alternative hypothesis. The null hypothesis is always there's no effect, there's no difference, there's no something, okay? And that the difference that's observed is due to random error. Because we know from central limit theorem that when we take a sample, those are going to vary around the true parameter. So there's going to be some random error, and the null hypothesis is saying that so any difference we're observing is due to random error. The alternative hypothesis, on the other hand, says no, that difference that we're observing is larger than we would expect to see due to random error. So in other words, that difference is real. It's not just random error. It's not just that we're seeing variation around the true value. It really is something different. The null hypothesis is usually the current state of things, and it's usually the statement that the researcher is trying to disprove. And this is a different way of thinking about things than we're used to in a lot of situations. The alternative hypothesis is actually usually the main one, in the sense that it's what the researcher generally wants to show. So alternative has some kind of sounds like it's secondary in some way, but it's not. It's usually the main one. Quality control is the exception, and we'll look at that when we get to an example. With quality control, it's not that they want the alternative hypothesis to be true, but it's that they need to take an action if it is. So the null hypothesis, being that it's usually the current state of something, we start off assuming that the null hypothesis is true. So as I said before, like starting off saying something is true and trying to disprove it is a different logical process than you see in something like a mathematical proof that you've seen in geometry, where you take things step by step by step, and in the end you prove something is true. Okay, here we're starting off believing something's true, and while this may not be a familiar logical process to you in math problems, it's not totally unfamiliar, because it's really the same kind of thing we do in our court system, where we have a defendant who we assume that they are true unless we find evidence to the contrary. So the null hypothesis is like the defendant, that we're going to assume it's innocent until proven guilty. Okay. And proven guilty is we're going to look at the data to see if there's evidence against the null hypothesis. Okay. Now, we can never prove with 100% certainty that the alternative is true, okay? But when we find evidence against the null hypothesis. So it's like when we're finding the null hypothesis guilty, okay, what remains is the alternative. So in that case, we would say that the data supports the alternative if it appears like it could not have happened under the current state of things that we're starting off assuming to be true. The null hypothesis is denoted with an H with a subscript of, that's actually a subscript of 0. And I'm using the notation of the alternative to be H with a subscript of A. Okay, some textbooks use it to have a subscript of 1, but I've chosen to use the other common notation, which is H with a subscript of A for alternative, because I think that's more intuitive. The null always has an equal sign in it, and but for the alternative, we have 3 choices. It can either be less than, greater than, or possibly a not equal to. On page 148 is the hypothesis testing steps. And today we're going to concentrate on this first step of stating the null and alternative hypotheses. And we'll go through these sub-steps. It will be easiest if we do that while looking at an example. So I am now going to go over to the Orange book. But you can keep both books open. So, like I said, have your blue book open to page 148. And in the Orange book, I am on page 57. And so let's start with the, we'll work on this in-class exercise. We'll do the first 2 together. And then you can do the remaining ones, attempt those on your own. So first step, and I guess we could call this step 0, is just to write down H0 and HA. The H0 for the null hypothesis is sometimes called H0, so you might hear me say that, and that's what I mean when I say H0. So these are colons, and please note, these are colons here, not equal to signs. Step A is which hypothesis is being tested. Are we testing something about a population mean, which was mu, or something about a population proportion, which is P? So in this problem, it says in a standard drug treatment, about 35% of patients experience headaches as a side effect. So that tells us that they are testing proportions. So we're going to put a P here. So a couple of notes here. The first note is that notice the same parameter in both the null and the alternative. So P and P, same parameter. The second note is, so there's only parameters here. We have a P, it could be a P or a mu for means. So only parameters, no sample estimates. So no P hats, no X bars. The next step is to put an equal sign in the null hypothesis. And that is what is step B. Equal sign in the null hypothesis. The next step is, what's the null value being tested? Like, what is the current state that they're going to test and see now if there's any difference from this initial value? So in a real life situation, like that's where we're setting up the hypothesis. In a real life situation, we haven't seen sample data yet. However, in a textbook situation, the sample data like always follows right after that. And so it's really tempting to just like look ahead into that sample data and try to work that in the hypothesis. But remember, like, unless you have a crystal ball, in real life you haven't seen this. So it's best just to cover it up, like with your pencil. We're not gonna like cross it out, but cover it up and just don't look at it when you're setting up the hypotheses. So don't put the sample data in the hypotheses, and often when you cover that up, the value that you do want to include in the hypothesis is the only one left. Okay, and this says in a standard drug treatment, about 35% of patients experience these headaches. So that's the value that we wanted to put in our null hypothesis. And I'm going to put the decimal in because we'll need it later in our calculations. So this right here is step C. So step D is asking what direction is being tested. And that's going to tell us whether to put a less than, greater than, or not equal to in the alternative. So we have to look for a directional word. We have a lot of directional words in the English language, so I can't provide you with a comprehensive list. So we just have to read through it carefully. So this says standard treatment, 35% get headaches. A new modification of the drug treatment is tested to see if it reduces the side effect. So reduces is our directional word. Okay, and that tells us that we're going to put a less than sign in our alternative hypothesis. Less than for reduces. And the step E tells us to just put the same value in the alternative as in the null, okay? So we have the same value here. And I guess that is step E. So if you look, the two hypotheses are the same parameter, same value. Null has an equal, and the alternative has a direction. So let's look at the next example, and we'll start off with our step 0. Down null and alternative with colons. And so now let's read through this. A box for a certain brand of cereal should contain 10.25 ounces. Overfilling is undesirable because the company will lose money. But underfilling is also undesirable because the customers will be dissatisfied. A simple random sample of 25 boxes shows a sample mean of 10.1 ounces with a standard deviation of 0.29 ounces. Okay, so step A, are we testing means or proportions? So, a couple clues here. Okay, we don't have any percent signs. 10.25 ounces sounds like a mean. And we have like the sample mean being tested, being what's testing that 10.25. So our parameter that's going to go in here this time is mu for population mean. Okay, same parameter in both. Next step, always put an equal in your null hypothesis. Okay, next step is what is the current state? What is it that they're testing? And if we cover up that sample data, what we'll see is like there's only one value left, which is this 10.25 ounces. So that's what goes down in our null hypothesis. Next question is, what symbol do we want to put here? Okay, so remember we have three choices, and those three choices are less than, greater than, or not equal to. So we're going to look for our directional words, and if we're looking through here, we have over, overfilling. Over is a directional word. Okay, and underfilling is also a directional word. So we actually want both of those directions. So that tells us that we should use a not equal to sign. And then our last step here is put the same value in both the null and the alternative. So that finishes up that example. And at this point, you should pause the video and finish up the number 3 and the ones on the next page as an in-class exercise. So pause the video and work on that, and then we'll come back and do them all together. Okay, so for number 3, let's go over these answers. And here we are looking at, it says the article says that 20% of college students get a flu shot, but you think the percentage at UMF is higher. You take a simple random sample. Okay, remember we're not going to look at that data. So what's being tested here is population proportions, P, equal sign in our null hypothesis, and the current state. If we cross off our sample data, what we're left with is 20%. So we're going to put 0.2 here. I'm going to go ahead and just put the 0.2 here. And what is our directional word? Okay, but you think the percentage at UMF is higher. So that's our directional word. And that says we're going to use a greater than sign. Okay, on page 58, looking at number 4, it says nutritionists recommend that the daily intake of fat should not be greater than 30 grams. A simple random sample of 64 middle-aged men on weight control programs was taken to determine if the mean fat intake exceeds the recommended 30 grams a day. Sample mean was 37 and standard deviation was 32. Okay, so are they testing means or proportions? Okay, there's no percentage signs, and we can see that they're measuring things. So that tells us we're testing mu, the population mean. Always have an equal sign in our null. And what is the current state? What's the value that they're going to be testing against? Crossing out our sample data here. And what do we have left? There's two numbers here, 30 grams, 64 middle-aged men. 64 is our sample size. And so our current state is this 30 grams. Okay, so that's the value in the null. Same value in the alternative. And now what's our direction? what are our directional words? Well, it says it should not be greater than. And that says they're going to test and see if the mean fat intake exceeds the recommended 30 grams a day. Okay, so exceeds tells us that we're going to use a greater than sign in our alternative. Okay, in our next example, it says before an election is taken, before an election, a poll is taken by a nonpartisan organization to see if the voters have a preference between two candidates. In a sample of 300, 53% prefer candidate B. So means are proportions. Okay, we see we have a percentage here and nothing's being measured. So that tells us we're going to be testing population proportion. Always put an equal sign in the null. And now, if we cross off our sample data, there's nothing left. So what is our null value? What are they testing against? Okay, so as a hint, there was a hint here, and the hint said, if there's no preference, people could determine their vote by flipping a coin. Okay, so they're testing to see if there's a preference. There's no preference. So our null is, remember the null is always something. The null here is no preference. And if there's no preference, then, and people were flipping a coin, then each candidate would get 50%. So 50-50 would be the no preference. Okay, now, so we can put a 0.5 in both. And now what's the direction? Okay, they're testing to see if there is a preference. Okay, so preference could be in either direction. It doesn't say if they think candidate A is going to be better, candidate B is going to be better. So that tells us we're going to do a not equal to, because it could go in either direction. Okay, and our next one says we're going to do experiments on learning in animals to see how long it takes for a mouse to find its way through a maze. The mean time to run a particular maze is 18 seconds. A researcher thinks that a loud noise will cause the mice to run faster. In a sample of 10 mice, the average time when a loud noise is sounded is 17 seconds with a standard deviation of 2. So this says the mean time to run a particular maze is 18 seconds. So that tells us that we're going to be testing mu, population mean. Always put an equal sign in the null. And what's the standard value that they're testing against? Okay, remember we're not going to look at this sample data down here. And so what we're left with is this 18 seconds. So that's the mean time to run that particular maze, and they're going to be testing to see if the loud noise makes them run faster. So we put that 18 is what goes into our null hypothesis. Same value in both hypotheses. And now what is our directional word? Okay, researcher thinks the loud noise will cause the mice to run faster. So our directional word is faster, and what's being measured is time. So what sign are we going to put right here? And it's tempting to just think faster, somehow better, greater than, but faster when we're measuring time means that the time will be less than. So our sign that goes in our alternative hypothesis is a less than sign. Okay, in number 7, it says to test if Joe has ESP, he's asked to guess the suit of 52 cards from a standard deck. He guesses 17 correctly. Okay, hint, the null hypothesis is that he does not have ESP. If he does not have ESP, what percentage would you expect him to get correct just by guessing? So this one is a little tricky for a couple reasons. So are they testing means or percentages? Okay, so he's going to guess 17 out of 52 correctly. So while it doesn't come right out and say percentage, that's not something that's being measured. It's not a mean. So it's something 17 out of 52. We're going to look at the percentage correct. So that takes a little bit of thinking there. So we're going to put P's in our hypotheses. Null always gets an equal sign. And there's a hint here that the null hypothesis is no ESP. So what percentage would he guess correctly if he did not have ESP? So I guarantee you that I can get the same percentage correct every time. And what percentage would that be? In fact, I guarantee you that I can get 25% correct every single time. And how would I go about doing that? And I do not have ESP, and I can get 25% correct every time. I would be able to do that just by, if I always guessed hearts, I would always get 25% correct. So again, put the same value in both, okay? And if Joe has ESP, then he better get more than 25% correct to demonstrate that he has ESP. So that's the end of this in-class exercise. So next, do the new WebAssign, setting up hypotheses, and that is due in 1 week on Monday, April 20 at 11:59 p.m. And that is it for tonight.